Hello, vintage computer friends, and welcome to another episode in my series of YouTube videos where we explore the 1980s educational computer systems from West Germany. Today we'll have another look at the 4-bit 1981 Busch Microtronic computer system, and we are following up with another recursive program, right? So we are going to implement a recursive version of the infamous Towers of Hanoi on this very limited educational computer system. And I know that in my last video I promised you to follow up with a recursive version of the Towers of Hanoi on the Cosmos CP1 computer, but it seems that I really first need to import my CP1 memory expansion from Germany before I can actually pull off that program. So I tried a couple of ways to implement a recursive version on the CP1, and due to the limited RAM space, right, of 127 8-bit cells, I wasn't able to fit a recursive version of the program as well as the stack into the memory. I tried 2 or 3 different ways of implementing basically the stack, right? But in the end, I ran out of memory for all 3 of those. So in the meantime, we will just, continue with the Microtronic and let's see what it takes to implement the infamous Towers of Hanoi on this machine. Well, and I'm saying infamous because if you studied, like me, computer science in the 1990s or 1980s, basically, and probably even before that, then many of the introductory computer science textbooks would have this Towers of Hanoi problem basically as an example of a non-trivial recursive algorithm, right? And so let me briefly remind you of the problem. So we have basically 3 packs, right, or 3 locations here on our table, A, B, C. And the objective is to move, this tower of disks from A to C, right? And or here I have that stack of coins, right? And you say, okay, so what's so difficult about that, right? I can just do it like this, right? But of course there's a catch, and that means you can only move 1 coin at a time, right? And the second rule is that you cannot put a larger disk on a smaller one, right? So that's an illegal move. So I have to move the disk number 2 or second coin to here, right? And then I can continue, right? So, and that way basically you'll have to find a sequence of moves that then finally moves the tower from A to C. And yeah, so an iterative version of this algorithm exists, but it is actually more difficult to understand than the recursive version. So the recursive version is very straightforward, right? And I mean, as always, it's divide and conquer, or divide et impera, right? And so the base case for the recursion is you basically just have 1 disk, right, or 1 coin, and in order to move it from A to C, I mean, you do just that, right? And this is of course what the base case here says, right? In that recursive function has 4 arguments, right? The disk you're moving, the source pack, the destination pack, and the spare pack, right? Initially that's A, C, and B, right? And we start with disk 2 here, so the disks are numbered 210, right? So if you're at the smallest disk, 0, right, then you just move it from source to destination, and this is what the base case of the recursion expresses here, right? Else, I mean, you have to divide the problem into a smaller problem, right, or actually in 2 smaller problems, and the way that goes is basically the recursive formulation says, okay, so you solve the problem basically for 1 disk, or 1 coin less, right? And basically you move this sub-tower basically of coins or disks to that location, your spare location, right? Your spare pack B. So you're moving it from source to spare, and you can use the destination now as a spare pack in order to achieve this if you need to, right? And then you're going to move the biggest disk basically from source to destination, right? And now you need another recursive invocation, right? You gotta move your sub tower basically of coins to here, right? And this is what the second recursive call here expresses, right? And so this is the recursive formulation of this algorithm. And now let's have a look how we can implement this on the Microtronic, right? And we already implemented one recursive function or program on the Microtronic. And the key is, of course, that you need to implement something like a value stack, right, or an argument stack, right? Because for the move tower, basically a function, right, you now have 1, 2, 3, 4 local variables, and you basically need to maintain them in a stack, right, so that they don't override each other. And secondly, if you're making recursive calls, right, and you got to return from these calls, then you got to return to any of these location, to either this or that location, right? And for this we need a return stack. And on the Microtronic, we are using its large register set, right? Because it has like 32 4-bit registers, right? And they are organized in banks, right? So we have a normal or foreground bank of 16 4-bit registers from 0 to F. And then there's a complete copy, right? A background bank, also from 0 to F, another 16 registers. And we can basically swap in the upper part or the lower part of this extra bank and swap it with our foreground bank, right? And so what we're doing is, in order to keep track of our value stack, right, and the local variables here, we are now using the background bank of registers, and we need 4 4-bit registers here, right? And the layout is very similar to the last recursive program that we programmed, right, where we needed 2 8-bit counters, right? And 2 8-bit counters are 4 4-bit registers, right? And here we also need 4 4-bit registers. And in order to implement something like a push, basically we are bringing the registers from this state into that state, right? And then now we have the uppermost registers available for a new stack frame, right, for the next recursive invocation of our function, right? Okay, but first let me give you confidence that this program actually works, right? And for that I'm going to start the program. It's already in memory, right? I loaded it over Pico RAM, right? From SD card into my RAM emulator, right, which is replacing the 2114 SRAM chip, right, and basically emulating it. So I can just load memory images, memory dumps into the Microtronic like this. And so let's start this program now, and let's do it for the base case first, right, for one coin. So Microtronic waits for input now, right, so I can put in the number of disks or coins. So for one coin, it now says it, okay, it's easy, just move it from A to C, right? And then it waits for a key press, and then it says you're done, right? Okay, good. So let's do a slightly more complicated case, and let's use 2 disks this time, right? And of course that is also still rather straightforward. So we move now disk number 1 from A to B. And then the next step is move disk number 2 from A to C, right? And then, I mean, I guess you see it coming. So we move disk number 1 from B to C, and again we are done, right? And so more interesting are of course the cases for 3 and 4 disks. And this is actually the max we can support, 4 disks, right? Because we need 4 variables, right? 4 local variables, and so we only have 16, right? So we exactly have space for 4 stack frames. So that's the maximum nesting depth of the recursion. But let's run it for 3 and see what we get. So we move 1 from A to C, which is surprising, right? 2 from A to B. And now we are moving 1 from C to B. Okay. Now I guess we are moving 3 from A to C. and we need to get 1 out of the way again from B to A. Now we can finally put 2 on top of 3 on C, and finally move 1 from A to C, and we accomplished our puzzle. Okay, so that program works, right? And let me also show you that it works for 4, but I don't have 4 coins here. But also notice that, you know, actually has to work quite a bit in order to get to the steps, right? Let's just step through that, and I double checked, so the solutions are indeed correct. And again, there is a iterative loop-based implementation of this puzzle solver, right? But it's actually harder to understand, and it also requires insight into the mathematical structure of the solution, right? And so it's harder to understand, as I said, than the recursive version. Let's have a look at the program and step through this, and this should be faster than last time, right? Because the basics of how to implement a recursive function or program on the Microtronic I have already explained last time, right? When we implemented the recursive summation program that sums the first n natural numbers. Again, we start by clearing the register file, right? All registers are set to 0. Then FOE basically now brings in the upper bank from registers A to F from the background register set into the foreground, right? So that we can actually write our values into them. So we need to make the first call to the Hanoi function, to the main function, right? And we got to supply our arguments there. So we will see how we are using the registers. First we turn on the display, so we are displaying register F, and we are waiting for keypad input here, right? So the program starts by asking the user basically how many disks do we want to play with, right? And so that is the number 1, 2, 3, 4 that goes into the F register, right? So then we are clearing the display, right? FO2, because the machine runs faster then. Now we are loading in the source, destination, and spare pack names, right? So looking at our program again, we have the disk argument, we have source, destination, and spare, right, as arguments. So, and the source argument will be in register E, and the source pack is A, right? So we are loading A into register E, and then we are loading the destination pack into register D, which is of course C, and in register C we have the spare pack name, which is pack B, right? So we have now set up basically the arguments for the first call. We are bringing back the ordinary register set, because we also need to set up the return stack, right? So basically we make a function call, and when that call returns, we want execution of the program to continue at a certain point, right? So if the call to the function is here, COD, right, then we want it to continue at this point. And for this we are using the technique I also discussed last time. Since we do not have indirect addressing, right, so we cannot put an address for program continuation onto a stack, but we are emulating a return stack and program execution and jumps basically by using numeric labels, right, numeric markers, jump labels. So here we are loading the first numeric label 1 into the F register, and like in the last recursive program we implemented, we are using the upper register bank in the normal register set, the foreground register set, F, E, D, C, B, basically for the return stack growing down from register F, right? So, and when the Hanoi function returns, basically it executes a piece of code that I'm calling the jump block. This jump block basically looks at the top of the return stack, right, into the F register, looks at the numeric label, right? And if it finds the label 1, then it will simply branch to address 0b, right? Because this is where the continuation is, right? Or if it finds another label, say label 2, then it might jump to another address, right? So it's a fully general method, but you need to set up the jump block and by hand basically put in the right continuation addresses. So now at COD, this is goto, right? So we have prepared the value stack and the return stack now, and we can simply make the first call, right, to our Hanoi function, right? And as I just said, when this returns, then the jump block, because we have set up the right numeric return label, right, on the return stack, will continue here. And all it does is basically it halts the program right after it briefly turned on all 6 segments of the display. So that's actually an unnecessary operation here, but this simply halts the program then when it's done. Okay, so let's get into the main definition of the Hanoi function, right? And so we have to implement this now, right? So again, we have the disk in register F, right? We have source in E, destination in D, and spare in C, right? And this is our value stack. And we can always access basically our value stack by windowing in, basically exchanging, swapping in the background, the upper bank of the background register set, right? And that's actually the first thing we are doing using the FOE opcode. Excuse me. Using the FOE opcode, we are bringing in the upper bank of the background register set so that we have access to the arguments, right, to the Hanoi function call, the value stack, this top frame of the value stack. And next, we are now actually checking if we are at the base case of the recursion, right? And I didn't use disk 0 here, but I used disk 1, right? So we do a conditional branch now, right? So if it's greater than 1, then we have the inductive case of the recursion, right? And we do a jump here, then we are jumping to there. Else we are now in the base case, right? And all we got to do for the base case basically is, you know, we already now have the disk in our you know, value stack. We have source and destination. All we have to do is basically display what's on the value stack, right, on in the top frame, basically to show us to move disk from source to destination, right? So we are basically turning on the display and we are displaying these 3 registers, D, E, and F, and that will reside basically on the left. You will see the disk number from F, right? And then you will see the source and the destination pack basically being displayed, right? So yeah, that's basically all there is to it. And then we are waiting for keypad input, and then basically the program turns off the display again. We are bringing back the normal foreground register set, and then we actually now need to return basically from the base case of the recursion, right? And for this we have a jump to the jump block here, go to B0. This is where the jump block starts, right? And like in the last program, the recursive summation program, the jump block basically simply checks now the top of the return stack in register F, right? The foreground set register F, whether it contains one of these numeric jump labels, right? So if it contains a 1, then it continues at address 0b, right? Which was, we already discussed this, this was after the first main call to the Hanoi function, right? Else if it contains a 2, then it jumps to 24, and we are not there yet, right? But let's continue going through the program. So this is basically then the end, a return from the base case, right? Just does a return by jumping into the jump block and branching accordingly from there. So else we are now at address 15, right? And remember that here we did a branch, we branch to 15 if the disk number is greater than 1, right? So we now have the recursive case, the inductive case. And looking at our program again here, we have to make two recursive calls, right? The first is, recursive call to the function itself with disk -1, and basically by shuffling around the source, destination, and spare packs into source, spare, destination, right? Then we move the disk, and then we do another recursive call, right? So let's prepare the first recursive call. And for this, again, we of course have to set up the value and the return stack now, right? So we first bring in the upper bank of the value stack, so we can put our values in there for the call. Then we now have to actually make space, right? So we got to do the push operation. So what we're doing now is we are moving down basically the upper frame, the upper 4 registers by 4 registers, right? So basically this register here, F gets copied to B, E gets copied to A, D gets copied to 9, C gets copied to 8, right? And this is what basically 4 calls or to B70 are doing, right? So, all right, we now made a space on our value stack, right, by pushing basically the registers down. So we have this row available, registers C to F, and we now need to supply the right arguments to make the recursive call, right? And if you look at the first recursive call, of course, we need to supply disk -1, and then we need to shuffle basically the arguments a little bit around, right? Because instead of destination, we need spare, and instead of, right, and vice versa. So, but source remains the same. So we bring back the upper bank of the value stack, so we can supply the arguments in that stack frame on top, right? And we are simply copying now over the old argument, the old disk number, right, from B to F. But we then need to subtract 1, right? And this is what 71F does, subtract 1 from the F register. Now we have disk here, right? And disk -1 here. And so the source argument of the recursive call stays the same, right? So we can simply copy A to E. And then we need to shuffle things around a little bit. So we copy 9 to C and 8 to D, right? And we bring back the normal register bank. Yeah, and now we gotta also set up the return stack. For this we have another subroutine basically which moves now the return stack down, right? So we can do the push. That means the current top of the return stack is an F, right? So F goes to E, right? E goes to D. Actually we do this the other way around, otherwise we would override registers, right? So we need to move 9 to 8, A to 9, B to A, and so on. Finally F to E, then F is available, and we can put our numeric continuation marker in there for the return stack, and this time we are using marker 2, right? And what that means is when the jump block is executed, right, to implement the return from the function call, it will find the 2. Look again at the jump block, right? So the jump block is at B0. So if it finds the 2 on top of the return stack, then it goes to 24, right? But before we can execute the move disk from source to destination, we need to get access to the original arguments, right, to that function call, right? So disk, source, destination, and spare, right? And given that we made the recursive call, we now have the value and return stack in this situation, right, in this condition, and we need to get back to this condition here so that we have access to the original argument, right? And to do so, we first pop the return stack using B60, right? And then we are popping the value stack 4 times. And now that we have access to the original function arguments again, we can simply swap in the value stack, right? Turn on the display, and again simply display registers D, E, and F, right? So we will see the disk number and the source to destination on the display, right, corresponding to move disk from source to destination. And then we are again waiting for keyboard input, right? So we turn off the display and we then continue basically by doing the second recursive call here, right? And that's basically the same story as the first recursive call. The only difference being that, you know, the pack arguments are being shuffled around again a bit. But it's basically same story, right? We are preparing the second recursive call. Again, we are creating a value stack frame by shifting it down 4 times, right? And we are bringing in the value stack frame. Then we are copying the disk number. We are subtracting 1 from the disk number. And now we are shuffling the pack arguments around, right? This time A goes to E, 9 goes to D, right? And A goes to C. And we restore the normal register bank. And now we also create a return stack frame. And we use our third numeric return label now, number 3. And now we can finally make the recursive call. And when this returns, right, based on return marker 3, it will return to this address. And we are basically at the end of our function now, right? So there's only the end if here, but we still need to do something, right? We need to return from this function actually, right? Which means execute the jump block. And in order to do so, we of course need to clean up the stack. That means we pop the return stack and we pop the value stack 4 times. And then we go to the jump block, executing the return and hence continuation of the code at the right address. Yeah, and that's it, right? And then the only other routines are the same as the ones that I showed you in the recursive sum implementation video, right? So basically the stack manipulation subroutines that push and pop the return and value stack and the jump block at B0, right? But yeah, so that's the program. One more run. And success. Yeah, and it also works for 4, but this is a max as mentioned because we don't have more stack frames. And yeah, I kind of feel that this was probably my last Microtronic video. It seems that I reached the pinnacle of my Microtronic programming career, so to speak, right? Interestingly, I got this machine almost exactly 40 years ago, right? I started programming on this machine in January 1984 after I got it in Christmas 1983 from my parents. And I can still recall how I struggled basically understanding getting into programming, right? Learning this machine language, even simple things like, you know, distinguishing operations for greater than and smaller, right? Or greater and smaller. So things I can of course laugh about nowadays, right? But this machine launched my career into computer science and nurtured my interest in computer science. So I studied computer science then and eventually got a PhD. And yeah, I always thought that it is probably impossible to implement a recursive function on the Microtronic, right? And at least I had the impression when I learned about recursion for the first time in university, right? That must have been around 1992 or so, right? I started as a freshman computer science winter semester 1991-92, and we learned the basics of Scheme, Prolog, and Lisp programming and all that, right? Where recursion is big, of course, especially in Lisp or Scheme. And I thought, is it possible to implement something like this on the Microtronic, right, with its limited instruction set? And back in the day, I think I was pretty convinced that the answer was no. Alright guys, so that's the last Microtronic video, at least for a while, right? And once I get my Cosmos CP1 memory expansion, I will still implement the Towers of Hanoi on the Cosmos CP1 machine. But that's going to be, end of March or April. So long until then, and stay tuned. See you then, right? Bye. Thanks for watching.